We want to keep talking about integration by parts. We introduced the anti-product rule yesterday. The nice thing about integration by parts is that there's a formula for it. The integral of u dv is uv minus the integral of v du. The unfortunate part of integration by parts is that there's a formula for it. A lot of times formulas are false comfort. Oh, I'll just look up the formula. But this is a formula that requires you to do some work. There's a lot of stuff that goes along with this formula. So the first thing you want to do is identify your givens. There are 4 parts in the parts formula: u, du, v, and dv. Over on the left, this is the integral we're starting with. Those are the given parts. And we get to decide what is u and what is dv. So u, and then the other part is dv. This is a choice that we're making. The only thing that we have to remember is that dv needs to be something we can integrate. dv must be an integral that we know. That's the only rule we got right now. Must be something we know the integral of. Oops, I spelled must wrong. This is what happens when I have 8 o'clock classes. There are plenty of ways to find out what you should put in the u and what you should put in dv, some even mnemonic devices for it. That's attempting to make the process robotic, and the more robotic we make the process, the less we are trying to understand the process and just trying to get the answer. If our goal is just to find integrals, we'll ask Wolfram Alpha what the integral is. If our goal is to understand the process, we need to watch the process in action, not follow some program. As I say that, of course, is I write down the steps that you're supposed to do. Yeah. Once you have the 2 givens, you need to find the other 2 parts. We differentiate u to find du, and we integrate the v to find dv to find v. That's why dv must be something that we can integrate. You already know how to integrate it. Then we can put together in the parts formula. And then we evaluate the secondary integral. And then repeat as necessary. Creating the handy mnemonic GFFSR. Sir. I don't think that's that helpful. I'm not good at mnemonic devices. My mnemonic for trig functions is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I might not be very good at the mnemonic device thing. Of course, before we begin this process, we want to verify that we're not dealing with substitution. Even though parts is going to be your favorite method of integration, always start off and make sure this is not a substitution problem. The sneaky thing here is this is an iterative process, and this integral of v du, this is our secondary integral. So this is what I'm referring to as the secondary integral. The reason that we say repeat at the end of the process, it hasn't come up because we've done all of one example. The reason that we say repeat is sometimes the secondary integral is a parts integral. When you go through the process again, I still call it a secondary integral because I don't know what comes after a tertiary. Tertiary? Third one. And I haven't come up with a replacement for secondary integral. So, if you recall, yesterday we integrated x times sine x dx. The first thing that we want to do when we plan on integrating by parts, we have to make sure that our integral is not a substitution. So for example, if I have x times sine of x squared, this is a substitution. The x squared is inside the sine, and that x is hanging out front to be the derivative of the inside. So first we want, before we even begin, we want to see this is a substitution. That x and the x squared tell us that this is a substitution integral. The derivative of the inside is a 2x. So that's going to make a 1/2 because I don't have a 2 on my x out here. So we're going to get a, and the thing that we're integrating is sine. So we're going to have a 1/2 cosine of x squared, a negative cosine of x squared plus c. This is where we want to be with our substitutions, our nice straightforward substitutions like this. Not the ones where we have to do some weird back substitution and double substitute. But like our nice straightforward ones, we want to recognize when that happens so that we don't have to write down a lot of details. Let's go on to parts example number 2. The first thing that we want to notice is we see an x squared and we see an x. But the problem is we don't have a factor of x to be the derivative of the x squared. The x that we see is inside of a sine. I don't have some factor of x. I've got sine of x. I don't have an x to be the dw. So right away we can see that this is not substitution. Since it's only week 3 of our Calc 2 class, if it's not substitution, it's parts. Those are kind of your only 2 options right now, because I haven't done a lot of the weird algebraic stuff. What we learned yesterday with x sine x is that it was handy to put x in the u position. Take the derivative and come down to 1. When we put sine in that place and x in the integral spot, even though x is something that we can't integrate, it made things bigger. When we integrated x, it became an x squared. That made things worse. So let's follow that same plan. Let's set u as x squared. That means dv will be the sine of x dx. So we've made a choice with our given parts. Next, we need to find the other two parts. Differentiate to find du, and integrate to find v. Once we have all four parts, we can put together in the formula. So the integral of u dv is uv minus the integral of v times du. Since I got a negative cosine, I have a factor of -1. I'm just going to pull that out and make the integral, make the minus into a plus. Next, we're at the secondary integral, which means we're going to repeat this process. There's 2x cosine of x. This is another parts problem. So it's a 2-for-1 deal. We get to do parts again. At this point, you might wonder, why did I leave the 2 in the integral when normally I pull my constant factors out of the integral? I have secret reasons for this. So let's do parts again. And we're going to make the same decisions that we did last time. If I put u in the x, or the 2x in the derivative spot, then the derivative, then that's going to make things smaller. Derivative of 2x is just going to be a 2. So my secondary integral is just going to be a sine. So I like that. That sounds like a good plan. If u is 2x dx, oh, the dx always goes with the dv. If u is 2x, then du is 2 dx. If I choose u to be 2x, then the dv will be cosine of x dx. Since we're just started on this process, I'm including the dx always with the dv and then getting rid of it when we integrate. And then the dx shows up when we find du. So the integral of cosine is sine. So then now we get v is sine of x. It's sine of x plus c, but we can use whichever antiderivative we want. Let's use the one where plus c is equal to 0. Still got this first term, so I'm going to have minus x squared cosine x this minus became a plus. I need to drop the color coding, but I can't stop. I'm going to write parentheses because I know that the secondary integral takes up 2 terms. The integral of u dv is uv minus the integral of v du. And I'm going to add the next 2 terms, so I'm going to use parentheses. Since we're just adding what's in the parentheses, it won't matter. But eventually that's going to be a negative out front. You're going to forget the negatives and your third term will be the wrong sign. So be careful. Now I'm going to do uv minus the integral of v du. So 2x sine x. I really needed to drop the color coding, but I can't stop. Minus the integral of v times du. Now we have a secondary integral that's nice and straightforward. The integral of 2 times sine x dx. So the integral of 2 times sine x dx is -2 cosine of x. Is that okay? This seems like a lot of writing because it's a lot of writing. We had to do parts twice before we got down to a secondary integral. That was just no technique required, just no stuff. We were 2 integrals in to when we had to know stuff. Our secondary was a nice simple integral. But we can look at the secondary, since we're doing parts, the secondary integral can be done by parts again. So note, we didn't have to. In this case, our secondary integral, we didn't need to use parts again. But that doesn't mean that we can't use parts again. I have a reason for wanting to use parts again. In this case, we're going to do the same strategy that we used in the previous 2 uses of parts. I'm going to put the polynomial part, in the derivative location. So u is equal to 2. That's going to make du equal to 0. So we're going to do uv minus the integral of v times 0. And that thus ended the parts. So we don't have to use parts again, but let's think about using parts again. I'm going to set u to be the 2x. Sorry, u to be just 2. And then du is 0. This means that dv will be sine of x dx. And v will be negative cosine. This means that our next term will be uv minus the integral of v times du, but that integral of v times du will be 0. So I'll still have this term x squared cosine x plus 2x sine x minus the integral of 2 sine x dx. And that will be built with uv minus the integral of v times du, which is getting multiplied by 0. So we can not bother calculating the integral of 0 cosine x. That's where our plus c is going to be. That's just going to be integral of 0. That's just going to be some constant. Also, we can see the two negatives cancel out to make the positive. Notice that we did parts 3 times, starting with x squared and sine x. Then the second part started with 2x and cosine x. And our third parts started with 2 and sine x. The start of subsequent part, or the end of our first part, is the start of the second parts. The end of the second part is the start of the third part. The next iteration of parts picks up where the last one left off. End of first parts is the start of the second parts. End of the second parts is the start of the third parts. This may sound obvious, but it's like totally not like this in storytelling. The end of Empire Strikes Back was most definitely not the beginning of Return to Jedi. There's like a whole bunch of stuff that went on in the middle. So, because we want to do less writing, the goal of math class is to stop writing all this friggin' math all the time. We're going to combine all of our parts. We're going to do all our parts at once, because this just keeps going on. So let's see what it looks like when we're going to do all the parts at once. It starts off like it always does. You see, we got x squared and sine of x. We already know that this is not substitution. Since it's not substitution, this is week 3 of calculus class. We're going to do integration by parts. We make our decision normally. Say, we're going to do parts. And I see a polynomial as one of the parts, so I'm going to make u that polynomial. And that will mean dv can be the sine of x dx. Oops, I spelled dv wrong. And then before we begin, we say, oh, I see where this is headed. The first du is a 2x, and our first v is negative cosine x. So at this point, we stop and we say, we see there where this is going. The secondary integral is going to be u equals 2x, and dv is cosine x. This 2x is going to become my next u. This negative cosine x is going to become my next dv. So here's what we're going to do. We're just going to differentiate all the way down to 0. I don't want to alternate. The derivative of 2x is 2. The derivative of 2 is 0. And for each of those derivatives, we get an integral in the other column. All parts at once means we differentiate down to 0. Differentiate down to 0 and integrate for each of your derivatives. Now we're going to pair up all the UVs. We're going to do a UV, and then a UV, and then a UV. So our first term is going to be negative x squared cosine x. Our next term is going to be 2x times negative sine x. And our last term is going to be 2 times the cosine of x. Now remember the parts formula. You'll notice that I didn't fill in that last sign, and you'll also notice that it wasn't minus 2x sine x, it was plus 2x sine x. This is because the parts formula is uv minus the integral of v du. So what we're going to do is we're going to alternate, keep the sign, change the sign, keep the sign, change the sign. So we're going to keep the sign here, change the sign here, keep the sign here, and then we're done. We alternate, keep the sign, change the sign, because the parts formula is uv minus the integral of v du. And if that v du is parts again, it's going to be uv minus, uv minus, uv minus, uv minus. And so every other one, the negatives cancel out and become positives. So in an infinite parts. So the U2 V2 gets to change the sign. U3 V3 has 2 negatives, so we keep it. U4 V4 will have 3 negatives, so we change it. So this one gets a keep. This one gets a change. This one gets a keep. This one gets a change. And so on. How's everybody okay? I don't like writing multiple parts. That's why I immediately teach just multiple parts right now. Do all the parts at once. Helps us understand the procedure. We differentiate down to 0. If we think of it in those terms, this only works when we have one of our factors that's a polynomial, and the other factor, our other part, is something that we can integrate. So our 2 rules have already got us seeing where this works. So this shortcut was only going to work if one of our parts is a polynomial that will differentiate down to 0, and our other part is something that we can integrate. So here's an example where this shortcut will work. One of our parts is 5x to the third. The other part is an e to the 2x. 5x to the third will differentiate down to 0. E to the 2x is something that we know how to integrate. So multiple parts is a go. We're going to start. U is going to be the 5x to the third. And our other part is an e to the 2x. We're going to differentiate down to 0. The derivative of 5x to the third is 15x squared. For every derivative, we integrate, or 1/2 e to the 2x. The derivative of 15x squared is 30x. The integral of 1/2 e to the x squared is 1/4 e to the x squared. Or sorry, e to the 2x. The derivative of 30x is 30. The integral of 1/4 e to the 2x is 1/8 e to the 2x. And the derivative of 30 is 0. And our last one's going to be a 1/16 e to the 2x. Differentiate down to 0, integrate for each derivative, or write an integral for each derivative. Write down all the UVs. So we go down these diagonals. So we can see there's going to be 4 terms. Our first term will be 5/2 x cubed e to the 2x. Just because we're doing a shortcut doesn't mean we're going to write our terms like slobs. 5 times 1/2 is going to be 5/2. I'm going to gather that out in front. I'm going to put my polynomial part in front of my exponential function. The next term is a 15/4 x squared e to the 2x. Notice I did not write a sign in between, because they're going to be alternate. Keep the sign, change the sign, keep the sign, change the sign. If it was negative, I would put that down, because I have to know what I'm going to keep or change. Then a 30/8 x e to the 2x. And then 30/16 e to the 2x, and then plus c. Now we're going to go through and we're going to alternate. Keep the sign, change the sign. Keep the sign, change the sign. Oh, then we're going to notice 30/8 and say, oh, that's awful. And 30/16. And it's like, oh, ooh, that looks terrible. I should have fixed that while we were on our way, but I've already started drawing a box. So we're going to hope that Leach doesn't get mad that we didn't simplify our fractions. Actually, you're going to be typing these responses, so you can just go back and edit. So it's not that big of a deal. You can just go back and edit 30/8 to be 15/4. And your 30/16 can be 15/8. Now, when you go into Wolfram Alpha to check your answer, because you're going to go to Wolfram Alpha and check your answer, you're going to say that you took the derivative of your answer, and that's how you checked it. But really, I know the truth. You're going to go to Wolfram Alpha and say, hey, Wolfram Alpha, did I do this right? And you're going to look at what Wolfram Alpha tells you, and it's not going to look like this. You're going to say that Wolfram Alpha only wrote e to the 2x once. That's because Wolfram Alpha looked at this and said, I'm not typing that e to the 2x all that time. I'm going to factor that shit out. So a very common maneuver, since we've got all these e to the 2x terms, is to write this as an e to the 2x factored out and leave behind a polynomial. Oops. But then you're going to say, dude, I just checked this on Wolfram Alpha, and this is not the polynomial Wolfram Alpha was using. Because Wolfram Alpha is like, oh, dude, I don't want to be typing all these friggin' fractions. I'm going to pull the fraction out. And so I'm going to factor out, let's say, at the very least, a 1/8. But it looks like I'm probably going to factor out 5/8, because all those numerators have a 5 in them. And because our polynomial is going to end up in parentheses, I'm going to write the exponential part first as a coefficient for the polynomial, mainly because I've got this fraction running around too. So most likely we'll pull out a 5 from all the numerators, pull out an 8 from all the denominators, put the e to the 2x out front and say, get in the parentheses polynomial, and then write a polynomial with integer coefficients. I've taken out the 5, I've taken out 1/8, so our coefficient of x to the third will be 4. I took out a 5 and a 1/8. So I'm going to leave behind a 3, and I'm going to have to put in a 2. So that's going to be a 6. I hope it's 6 because it's going to be the same for these two. And I took out the 8 and I took out a 5, so it's just going to be a 3. If you're just writing it down, write it like it showed up. Just write it like it showed up with all the extra 2x's. If you just transcribe what you wrote and type that, just do that. Just do that. If you're going to do algebra, make sure you do all the algebra stuff. Check your answer on Wolfram Alpha. Did I factor out the fraction right? I don't know if I factored out the fraction right on this one. But I'll tell you that most computer systems will pull out the e to the 2x. They'll say that's a common factor. Let's just type that once. Any questions? It only seems like a lot to remember because it's a lot to remember. And you have to remember all of it all the time in perfect detail. There are more things that we can do with integration by parts, like integrating by differentiators, which is a cool trick. Well, we're out of time for today. That means we're out of time for this week. I will see you all on Monday, and I'll be in my office tomorrow. Everybody have a good weekend, and thanks for playing.